Let's see. So, uh, well, if you have, okay, why does momentum equal negative I h bar d over dt times the wave function? Well, if you let the wave function equal like this wave, let's say it's a sine wave, momentum with particles is equal to mv. And you can think of v as being the slope of the sine wave, because at this point the slope is the steepest, you have the fastest velocity here, and up here and down here the slope is zero, so you have zero velocity here. So it's kind of like being at the top of a hill and you slide down to the bottom. So your velocity is greatest right here. So it's the slope of the wave will give you the momentum in terms of a velocity. And there's no mass, so it's kind of replaced by a momentum. This wave, this kind of replaces the mass part of the equation, and the differential replaces the velocity part. Strictly, I mean non-strictly speaking. So that's why you can, this is kind of relates to the slope and to the wavelength. And then this is Planck's constant. This is an imaginary number. This is the square root of -1. That's a negative sign. And so if we take this thing's called like a comma b, and then that would equal ab minus ba. And if that equals 0, then that means that you can know A and B at the same time. There's no uncertainty if it equals 0. This thing's called a commutator. So now what happens if, okay, that's, so from here to here you can kind of think of as the momentum and the slope, and then x would just be some point somewhere on the curve. Somewhere on the curve, you can just think of x. So what would happen if you take x and momentum? Would you get 0? Can you know x, the position, and the momentum at the same time of a wave? And so let's do that. So this would be, well, let's not do that. Let's multiply it by the Schrodinger wave. What the heck? And what is the Schrodinger wave? Well, it's the wave associated with the particle. In the early days, the Bohr model had a nucleus and an electron going around the nucleus like an orbit. And that worked pretty good for like a hydrogen or something, but if you got into multiple orbits with lots of electrons, it didn't work very well. They knew that this was not correct. And then Schrodinger said, well, instead of using particles for electrons, let's use, wave and momentum and energy wells or something, and particles in a box or something. So that's what this is. Instead of having a mass, electron mass, you have like an electron wave, something like that. So then you wind up with these weird spheres for the S shell, and I don't know, something like this or something for the P, and then the F's got this weird thing. I don't know, it's really weird looking. And they're not even orbitals, they're like probability shells where you probability of finding an electron, and it's just really weird. It's called quantum mechanics or something. So that's what this is. This kind of represents these weird electron orbitals. This is the position on the wave, and this is the momentum of the wave. So the question is, can we know the position and the momentum of an electron within this Schrodinger equation? If we can, then this should come out to equal 0. That's a question. Will that happen? So let's do it. So let's take x, and then let's substitute what p equals in here. So instead of putting p here, Let's put what it equals in. That would be negative I h bar delta delta t. And then the wave equation. Alright, what's that equal? Well, that would equal, what would that equal? That would equal x negative I h bar delta delta t wave minus del I h bar delta delta t x the wave equation. Alright, ugly, very ugly. Let's move on. So then that would become negative x I h bar delta delta t that plus I h bar delta delta t x unser wave equation. So this part right here, that would equal I h bar 1, well, let's do this, x delta t this plus x delta delta t. Hee-hoo. But wait a minute, this right here is the negative of this right here. So you can cross this out. That just leaves this part right there. So what's the differential of x? That's just a 1. X differentiated is 1. So this equals I h bar 1 times the wave equation. So now you can say that x, let's just say p again, let's go back with p. The wave equation equals I h bar, the wave equations, cancel those out. So then you can just say that xp equals I h bar. That's not 0. That means you cannot know position and momentum at the same time. That is uncertainty. That is the Heisenberg uncertainty principle.